You look up into the night sky and you see nothing unusual, just stars. Maybe a planet or two. But hidden in the darkness, something from another star system is racing through our cosmic neighborhood right now. 3I Atlas, an interstellar comet. The third visitor we've ever caught from beyond the sun's grip. And after it passed behind the sun on October 21st, 2025, it came back changed, jets stretching 1 million kilometers toward the sun, a tale that shouldn't exist. Behavior that has astronomers worldwide checking their math. What exactly is happening with 3I Atlas after solar conjunction, and why does every new image make the mystery deeper? July 1st, 2025, the Atlas Survey Telescope at Rio Hurtado. Chile catches a speck moving against the stars. Within hours, pre-discovery images flood in. Zwicky Transient Facility has it from June 14th. Atlas itself tracked it back to June 5th. The object is 3R Atlas, moving at 61 kilometers per second relative to the sun. That's 140,000 miles per hour. Its trajectory is hyperbolic, meaning it's not bound to our star. It came from interstellar space, and it's leaving the same way. When David Jewett and Jane Liu aimed the Nordic Optical Telescope at it on July 2nd, they confirm what the survey caught. Clearly active, with a diffuse coma. The Minor Planet Center gives it the designation 3 on July 2nd, making it the third confirmed interstellar object, after 1 Oumuamua and 2 Borisov. By the time it gets its name, astronomers have 122 observations from 31 observatories. 3. Atlas is real, and it's ours to study for the next several months. If you value documented comet science and interstellar research like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. Also, this script is researched and factual, using sources from Avi Loeb's Medium posts published between July and November 2025, NASA Science Official pages updated through November 13th, 2025. David Jewett's Archive preprint 2510.18769, published October 21st, 2025 DARS, and ESA's official releases on ExoMars trace gas orbiter observations from early October 2025. These aren't generic sources. These are direct scientific observations, spacecraft data, and professional astronomer analyses published within days of each observation window. Now back to the information. Hubble Space Telescope locks onto 3I Atlas on July 21st, 2025. The comet is 277 million miles from Earth. Hubble shows a teardrop-shaped cocoon of dust coming off the nucleus. David Jewett leads the analysis. The imaging sets an upper limit on the nucleus diameter, 5.6 kilometers maximum, possibly as small as 440 meters. The coma extends in a broad fan along position angle 280 degrees roughly toward the sun, not away from it, toward it. Jewett's team notes this immediately. Quote, although described elsewhere as a sunward tail, the emission to the northwest is inconsistent with a tail produced by radiation pressure, but instead indicates anisotropic ejection towards the sun. That's the Hubble Science paper, published August 7th, 2025. Radiation pressure from the sun pushes particles away. Always away. But 3. Atlas is shooting material toward the sun in a fan pattern. Jewett attributes this to large dust particles, effective radius around 100 micrometers. These particles are 1 million times more massive than typical comet dust at 1 micrometer scale. Because their surface area to mass ratio is 100 times smaller, radiation pressure doesn't push them as efficiently. But here's the catch. To produce the same brightness, the comet would need to expel 100 times more mass in these giant particles than a typical comet sheds. That's an enormous energy budget for an object that's already strange. The rotation period comes next. Back in July and August 2025, multiple telescopes measure 3I Atlas, spinning every 16.16 hours, plus or minus 0.01 hours. Tony Santana-Ros and colleagues published this in August 2025, using observations from July 2nd through July 29th. Raul de la Fuente Marcos gets a similar period, 16.79 hours, from Gran Telescopio Canarias data, July 2nd through 5th. The comet is rotating. Every 16 hours, it completes one turn. Remember that number. It matters later when the jets refuse to smear. JWST observes on August 6th. The near-infrared spectrograph catches carbon dioxide, water, carbon monoxide, and carbonyl sulfide. The nucleus is emitting 129 kilograms of carbon dioxide per second, 6.6 kilograms of water per second, 14 kilograms of carbon monoxide per second, and 0.43 kilograms of carbonyl sulfide per second. That's the JWST data published in multiple preprints through August. Carbon dioxide is driving the activity, not water. At 3, I-Atlas's distance, carbon dioxide ice sublimates readily, while water ice stays frozen. Spherex observations from mid-August show the carbon dioxide coma extends at least 348,000 kilometers in radius. Only visible in near-infrared, NASA's Swift Observatory detects hydroxyl radicals on July 31st and August 1st, confirming water activity. But the water production rate is only 1.35 times 10 to the 26th molecules per second. That's 12% of what comet sighting Spring was producing at 229% of 3 Mubarak S. I-Atlas's solar distance. Water is there, but it's not the main player. Then comes the nickel. Very Large Telescope detects atomic nickel emission on July 20th, 2025. Cyanide follows on August 14th. Between July and August, VLT watches the nickel and cyanide concentrations climb steadily as the comet approaches the Sun from 4.4 AU down to 2.85 AU. By August 21st, EDMIs 3. I-Atlas is emitting 4.6 grams of nickel per second and 17.6 grams of cyanide per second. Nickel emission isn't unusual. 2, I-Borisov showed it too, but here's the anomaly. No iron, iron 1 vapor, which typically appears alongside nickel in roughly equal amounts when outgassing from comets, is absent. The nickel to iron ratio is off, way off, and the nickel to cyanide ratio doesn't match typical solar system comets either. It matches industrially produced nickel alloys. That's anomaly number 5 on Avi Loeb's list, published in his Medium post from October 25th, 2025. Not proof of anything artificial, just unusual chemistry that doesn't fit the normal comet template. The comet brightens. It moves through Sagittarius in early July at magnitude 17.5, then Ophiuchus at magnitude 16 by late July. August takes it across Ophiuchus, Scorpius, and Libra. September finds it in Libra, magnitude 12 to 13. It's getting brighter, getting closer, getting more active. Mars gets a front row seat, October 3rd, 2025. 3. I-Atlas passes 29 million kilometers from Mars. ESA's ExoMars Trace Gas Orbiter and Mars Express both turn their cameras skyward. ExoMars, TGO, uses its color and stereo surface imaging system. CAS is designed to photograph Mars from a few thousand kilometers away, not comets 30 million kilometers distant. But it works. Multiple 5-second exposures stacked together reveal the coma, a fuzzy white dot moving across the starfield. Mars Express catches it too. The data from ExoMars, TGO does something unprecedented. It refines the comet's predicted trajectory by a factor of 10. Triangulating observations from Mars and Earth reduces positional uncertainty dramatically. This is the first time astrometric measurements from a spacecraft orbiting another planet have been officially submitted and accepted into the Minor Planet Center database. ESA announces this on November 14th, 2025. The trajectory is now locked. Astronomers know exactly where 3 I-Atlas is headed. October 21st, 2025, solar conjunction. 3 I-Atlas sits on the opposite side of the Sun from Earth, hidden in the glare. 8 days later, October 29th at 7:47 a.m. Eastern Time, it reaches perihelion, 1.36 AU from the Sun, 203 million kilometers, just inside Mars's orbit. The comet is invisible to us. No Earth-based telescope can see it. It's behind 770 watts per square meter of solar radiation at that distance. If it's a fragile, weakly bound natural comet, this heat could break it apart. If it's something else, something more robust, it survives intact. We won't know until it emerges. November 5th, 2025, first post-perihelion images arrive. R. Naves Observatory in Spain and the Virtual Telescope Project both release images. They show a compact source of light, no clear cometary tail pointing away from the Sun. Avi Loeb publishes an analysis on November 5th. Quote from his Medium post. This is surprising in view of NASA's JPL report of a non-gravitational acceleration. JPL's trajectory fit shows 3. I-Atlas experienced a nudge, a push from outgassing, normalized to 1 AU. Loeb calculates that momentum conservation requires the comet to have lost at least 13% of its mass during perihelion passage. 13%? For a typical comet losing that much mass, you'd expect a massive coma with dust and gas. Blown into a classic tail shape pointing away from the Sun by radiation pressure and solar wind. But the November 5th images show nothing like that, just a fuzzy ball. Compare it to Comet Lemon from the solar system, imaged November 3rd by the same R, Naves Observatory. Lemon has a clear cometary tail pointing directly away from the sun. Classic comet behavior. 3. I-Atlas doesn't look like that at all. November 8th, 2025, 0410, Universal Time, M, Jaeger, G, Riemann, and E. Prosperi observed 3 I-Atlas at 29 degrees separation from the sun. They stacked 24 exposures in green filter, 35 seconds each, plus 2 in red and 2 in blue. The images reveal a complex jet structure, at least 7 distinct jets radiating from the nucleus. Some point toward the sun, some point away. The glowing halo extends 500,000 kilometers. Avi Loeb analyzes this on November 8th. The jets don't make sense for normal rotation. If the comet rotates every 16.16 hours, and material travels at 400 meters per second outward, you'd expect the jets to smear into arcs over the month it takes to traverse 1,000,000 kilometers. But they don't. The jets are tightly collimated, needle straight. November 9th, 0508 to 0523 Universal Time. Frank Niebling and Michael Buckner capture a stacked image using 2 telescopes, Tech 140mm at f5 and ASI 6 200mm. 5 exposures, 3 minutes each. The result is magnificent. Anti-tail jets extending 10 arc minutes toward the sun. That's roughly 1,000,000 kilometers. Regular tail jets extending in the opposite direction, stretching 3,000,000 kilometers. Loeb publishes the analysis on November 9th. The anti-tail jets only stop at a distance of 1,000,000 kilometers, which means their ram pressure exceeds the solar wind ram pressure out to that distance. The solar wind flows at 400 kilometers per second, 1,000 times faster than the expected 400 meters per second outflow from natural comet volatiles. Since ram pressure scales with speed squared equals the outermost mass density in the anti-tail must be 1,000,000 times bigger than the solar wind's density, a few million proton masses per cubic centimeter. That translates to a mass flux of 2 million kilograms per second per million kilometers square. Sum it over 10 million square kilometers of jet area, and you get a mass loss rate of 50 billion tons per month. Loeb calculated earlier that 3I Atlas has a minimum mass of 33 billion tons based on the lack of non-gravitational acceleration before October. 50 billion tons per month is more than the comet's entire estimated mass. Something doesn't add up. The jets maintain orientation. That's anomaly number 12. Loeb publishes this on November 15th, 2025. At 400 meters per second thermal speed, it takes a month for volatiles to traverse 1,000,000 kilometers. During that month, 3 I-Atlas rotates once every 16.16 hours. That's 44 complete rotations over 30 days. If outgassing is triggered by sunlight hitting ice pockets as the nucleus rotates, you'd expect a string of puffs separated by 23,270 kilometers. The distance material travels in one rotation period, 43 puffs along a 1,000,000 kilometer jet, like peas in a pod. The images don't show that. They show continuous, coherent jets. And worse, some jets point away from the sun, which sunlight-triggered sublimation can't explain. The ice would only sublimate when facing the sun, creating sunward jets only. Could the nucleus have fragmented? 2. I-Borisov split around March 12th to 20th, 2020 S. Roughly 3 months after perihelion, when it was about 3 AU from the sun. 3 I-Atlas reached 3 AU on August 15th on the way in, and will reach it again on January 11th, 2026 on the way out. Fragmentation is possible. But David Jewett and Jane Liu imaged the nucleus on November 11th, 2025. It's a single body, intact, no obvious fragmentation. If the jets are fragment trails, where are the fragments? November 11th, 2025. Jewett and Liu's observation shows 3 I-Atlas with a prominent elongation at position angle 106 degrees plus or minus 10 degrees. The projected sunward direction is 115 degrees. Close match. It resembles the Hubble image from July 21st, which showed an anti-tail pointing toward the sun. There's also a weaker asymmetry at position angle 301 degrees, close to the anti-solar direction of 295 degrees. The imaged region is about 500,000 kilometers wide. The distances 1.43 AU from the sun, 2.16 AU from Earth. The comet remains a single body with a sunward anti-tail even after perihelion. November 15th, 2025, Tirasak Thalawang in Rayong, Thailand, captures 3 I-Atlas with a 0.26 meter telescope. The image shows a prominent anti-tail along with 2 tails. Sunward direction is lower left. The anti-tail persists. Avi Loeb discusses 3 possibilities in his Medium post from November 15th. 1. giant dust particles roughly 100 micrometers in radius, as suggested by David Jewett and collaborators. These particles resist radiation pressure because they're so massive. But producing enough to match observed brightness requires enormous mass ejection. 2. Ice fragments rather than dust, chunks of ice that behave differently than refractory dust grains. 3. Technological thrusters pointing exhaust toward the sun, accelerating the comet away from the sun through tightly collimated jets that penetrate the solar wind because of high speed. Loeb notes that future spectroscopic data can distinguish between these. Natural outgassing produces characteristic speeds up to a few hundred meters per second. Artificial jets would show speeds above a few kilometers per second. The data isn't in yet. The energy budget tells another story. To sublimate 50 billion tons of carbon dioxide over a month requires 3 times 10 to the 18th joules. The sun provides 700 joules per square meter per second at perihelion distance. To absorb that much energy, you need an area larger than 1,600 square kilometers. That's a sphere with a diameter of 23 kilometers. Hubble's upper limit on the nucleus diameter is 5.6 kilometers. The required diameter for carbon dioxide is 4 times too large. For water ice, with higher sublimation energy, the required diameter is 51 kilometers, 9 times too large. If 3I Atlas is a single body that didn't fragment, the surface area doesn't match the energy needed to produce the observed jets. Either it fragmented into pieces we can't see individually, but which collectively have more surface area, or the energy source isn't solar heating alone. The 12 anomalies stack up. Avi Loeb's list, published November 16th, 2025, includes 1. Retrograde trajectory aligned within 5 degrees of the ecliptic plane, likelihood 0.2%. 2. Sunward anti-tail, not an optical illusion, observed July, August, and November. 3. Nucleus about 1,000,000 times more massive than 1 Oumuamua, 1,000 times more massive than 2I Borisov, while moving faster than both. Combined likelihood less than 0.1%. 4. Arrival time fine-tuned to pass within tens of millions of kilometers from Mars, Venus, and Jupiter. Unobservable from Earth at perihelion. Likelihood 0.005%. 5. A nickel-dominated gas plume with no iron and unusual nickel to cyanide ratio. 6. Extremely low content of certain refractory elements. 7. Carbon to oxygen ratio in the gas is 10 times higher than typical comets. 8. Very low water production rate despite evidence of water ice. 9. Nucleus size upper limit insufficient to explain dust production rate. 10. Sunward and anti-solar jets requiring unreasonably large surface area to absorb enough sunlight for sublimation. 11. Non-gravitational acceleration near perihelion, requiring at least 13% mass loss, but the object appears intact. 12. Tightly collimated jets maintaining orientation across 1,000,000 kilometers despite 16-hour rotation period. Multiply the probabilities. 0.2% times 0.1% times 0.005%. You get a number smaller than 1 in 10 quadrillion. That's Loeb's calculation from his October 25th Medium post. He's not claiming alien technology. He's quantifying how unlikely each feature is individually and collectively for a natural comet. The mainstream view remains that 3I Atlas is an active comet under solar heating, with measurements ongoing. David Jewett's October 21st preprint describes the pre-perihelion development, noting that the dust production rate varies with heliocentric distance to the power of negative 1.8 Dower, consistent with carbon dioxide driving the activity. The heliocentric index is unremarkable compared to solar system comets. The morphology changed from a sun-facing dust fan in early July to an anti-solar tail by late July, attributed to large dust particles ejected slowly at 5 meters per second, responding sluggishly to radiation pressure. Similar 100 micrometer grains appeared in 2I Borisov. But 2, I had a much smaller heliocentric index, 1.9, more asteroid-like. 3, I's index of 3.8 is more volatile-driven. November 10th, 11:31 p.m. Eastern Time. The Virtual Telescope project in Manciano, Italy, captures 3I Atlas with 18 separate 120-second exposures. The comet is 14 degrees above the eastern horizon. A bright 61% moon sits 70 degrees away. Despite the challenging conditions, the image reveals a sharply defined, luminous ion tail, dramatically longer and more structured than before. Gianluca Massi, founder of the Virtual Telescope project, notes the much more developed ion tail compared to earlier images. Ion tails form when solar wind ionizes gas molecules in the coma and sweeps them away from the sun. The direction is set by the solar wind's magnetic field, not by the comet's motion. The blue-green color comes from ionized gases, scattering sunlight differently than dust. The tail's growth is normal for a comet that just passed perihelion and is now in the solar wind's full force. November 16th, 11:53 to 12:23 Universal Time. Satoru Murata combines 24 exposures of 60 seconds each with a 0.2 meter Celestron Edge HD 800 telescope in New Mexico. The image shows multiple jets both toward and away from the sun. The sunward direction is lower left. The jet structure remains complex. Multi-directional iris and collimated. Avi Loeb references this in his November 16th post, asking whether the anomalies flag alien technology or an unfamiliar interstellar iceberg. He emphasizes that comet experts, trained on solar system comets, may be missing something genuinely new. Collecting evidence is a learning experience, he argues, not a finished product. The public appreciates science as work in progress when scientists show humility to learn. The speed question keeps coming up. When 3. I-Atlas was discovered within Jupiter's orbit. It was traveling 137,000 miles per hour. Gravity accelerated it to 153,000 miles per hour at perihelion on October 30. NASA's Facts and FAQs page, updated November 13th, 2025, confirms this. That's normal for any object on a hyperbolic trajectory diving toward the sun. Gravity speeds it up inbound, slows it down outbound. The non-gravitational acceleration is much smaller, a nudge from outgassing, not a dramatic speed change. Mainstream astronomers like Qicheng Zhang, quoted in space.com on November 7th, clarify that there's no solid evidence the coma changed color. The gas coma simply contributes more to brightness near perihelion. The blue-green glow is ionized gas, normal for active comets. The color buzz is media hype, not scientific mystery. But the jets remain. A November 9th image from Niebling and Buchner shows jets reaching 1 million kilometers sunward, 3 million kilometers anti-sunward. November 15th image from Thalaweng shows anti-tail plus 2 regular tails. November 16th, image from Murata shows multi-directional jets. These aren't fleeting features. They persist, they evolve. They don't match the standard comet playbook. David Jewett suggests large dust particles. Avi Loeb suggests the possibility of technological thrusters remains on the table until spectroscopic data rules it out. The International Asteroid Warning Network turns 3 I-Atlas into a community exercise, improving comet astrometry and reducing biases from fuzzy comae. Observing window runs November 27th through January 27th, with check-ins through early February. Both NASA and ESA stress safety. 3. I-Atlas poses no impact risk. It's on an unbound fly-through, closest approach to Earth. December 19th, 2025. At 269 million kilometers, R1.8 AU. Still far, still safe. ESA's JUICE spacecraft observes between November 2nd and 25th. JUICE is 64 million kilometers from 3 I-Atlas during observations, farther than the Mars orbiters were in early October. But seeing the comet just after perihelion when it's most active, JUICE uses cameras, spectrometers, and particle sensors. Data download is slow because JUICE is using its medium-gain antenna, while the main high-gain antenna serves as a heat shield near the sun. We won't get JUICE data until February 2026. NASA's Juno spacecraft around Jupiter will probe 3 R-to-R Atlas on March 16th. 2026 on from 53 million kilometers, too far to intercept particles from the jets, but still a valuable data point. Europa Clipper, Lucy, Psyche, Parker Solar Probe, Punch, and SOHO all have observation windows planned or completed. Webb, Hubble, TESS, SWIFT, SphereX, Perseverance, Mars, Reconnaissance Orbiter, and Curiosity contributed observations at various times. This is the most comprehensively observed interstellar object in history. December 19th, 2025, closest approach to Earth, 1.8 Uyo, about 170 million miles, 269 million kilometers. Telescopes with at least 8-inch apertures can detect it, not visible to naked eye, not visible in binoculars, but visible to amateurs with decent equipment and dark skies. The comet will be in Virgo. Rising before dawn, magnitude around 11 to 12, faint but reachable. After December 19th, 3. I-Atlas continues outbound. It passes 0.36 AIU from Jupiter on March 16th, 2026, 54 million kilometers, then it's gone. Hyperbolic trajectory carries it out of the solar system at the same speed it came in, roughly 58 kilometers per second relative to the Sun. It will rejoin the interstellar medium, the space between stars, carrying whatever secrets it holds back into the void. What do we know for certain? 3I Atlas is the third interstellar object confirmed to pass through the solar system. Discovered July 1st, 2025 by Atlas Telescope in Chile. Perihelion, October 29th, 2025 due at 1.36 AU. Post-conjunction images from November 5th onward show unusual jet structures, including persistent anti-tail features pointing toward the Sun. The jets extend up to 3 million kilometers and appear tightly collimated, despite the comet's 16-hour rotation period. Carbon dioxide drives the activity, not water. The nucleus diameter is somewhere between 440 meters and 5.6 kilometers based on Hubble observations. The object experienced non-gravitational acceleration near perihelion, implying at least 13% mass loss, yet appears to remain a single intact body in November images. 12 documented anomalies collectively have a likelihood below 1 in 10 quadrillion, if all are coincidences for a natural comet, ESA's ExoMars. Observations from Mars improved trajectory prediction by tenfold, where the first time planetary orbiter data entered the Minor Planet Center database for an interstellar object. The comet will make closest approach to Earth on December 19th, 2025, then exit the solar system permanently after passing Jupiter in March 2026. What remains unknown: the exact mechanism producing the sunward anti-tail, whether the jets are giant dust particles at 100 micrometers, ice fragments, or something else, why the nickel to iron ratio is skewed, why the carbon to oxygen ratio is 10 times higher than typical comets, whether the nucleus fragmented into multiple pieces too small to resolve individually or remained intact, what spectroscopic data will reveal about outflow velocities in the jets, whether future observations from JUICE, Juno, and other spacecraft will resolve the anomalies or deepen them, and whether 3I Atlas represents a new class of interstellar comet with properties we've never encountered, or whether it's something we haven't considered. Avi Loeb frames it simply in his November 16th post, quote, "Alien tech masquerading as a natural comet." The foundation of science is based on the humility to learn, not the arrogance of expertise. When comet experts argued that 3I Atlas must be a familiar water-rich comet as soon as it was discovered on July 1st, 2025, they behave like artificial intelligence systems which reflect their training datasets. My point is simple. The dataset that established comet expertise included icy rocks in the solar system. For an object from interstellar space, we should keep our minds open to the possibility that it is something we have not seen before. David Jewett, leading the Hubble analysis, says in the August 7th NASA release, "No one knows where the comet came from. It's like glimpsing a rifle bullet for 1,000th of a second. You can't project that back with any accuracy to figure out where it started on its path. This latest interstellar tourist is one of a previously undetected population of objects bursting onto the scene that will gradually emerge. This is now possible because we have powerful sky survey capabilities that we didn't have before. We've crossed a threshold." The Virtual Telescope Project, imaging on November 10th, calls it both a scientific milestone and a source of wonder. ESA's Colin Wilson, project scientist for Mars Express and ExoMars, notes on October 7th. Though our Mars orbiters continue to make impressive contributions to Mars science, it's always extra exciting to see them responding to unexpected situations, like this one. I look forward to seeing what the data reveals following further analysis. 3. Atlas could be 7 billion years old. Older than the solar system itself by 3 billion years. If it originated from the Milky Way's thick disk, it formed when the galaxy was younger. Stars were different, and planetary systems were just beginning to populate the cosmos. It spent billions of years drifting through interstellar space, untouched by any star's warmth, until it fell into the sun's gravitational well in 2025. We get one pass, one observation window, then it's gone forever. The November images capture something we may never see again in our lifetimes. An interstellar comet, freshly heated by perihelion passage, displaying jet structures that challenge every model we've built from solar system comets. The anti-tail persists in image after image. The collimation defies rotation smearing. The energy budget doesn't close. The chemistry is off. 12 anomalies, 10 quadrillion to 1 against all of them occurring by chance. Not proof, just improbability stacked on improbability. If you value rigorous science done in real time, subscribe. This is history happening now. Comment from which city you're watching the sky, hoping to catch 3I Atlas in your telescope before it vanishes. This script draws from Avi Loeb's Medium series spanning July through November 2025, NASA Science Pages updated through November 13th, David Jewett's October 21st preprint, ESA releases on ExoMars and JUICE observations. and dozens of professional astronomer reports published within weeks of each observation. We're watching the data come in live, we're watching scientists debate in public, we're watching one community say it's a normal comet with unusual dust, and another community say the anomalies deserve serious technological consideration. Both sides have receipts, both sides have numbers. This isn't settled. It's active, it's unfolding. December 19th approaches, the observation window peaks. Telescopes worldwide will point at Virgo's pre-dawn sky. Spectroscopic data will measure outflow velocities. Photometry will track brightness changes. Imaging will reveal whether the jet structure evolves or stabilizes. And in February 2026, JUICE data arrives. High-resolution spectra, particle counts, multi-instrument cross-checks. Then in March 2026, Juno's flyby adds another perspective from Jupiter's neighborhood. By spring 2026, we'll have the most complete dataset ever assembled for an interstellar object. It won't answer every question, but it will constrain the possibilities. It will rule out hypotheses that don't match observations, it will narrow the field, and if the jets maintain collimation, if the spectroscopic data shows velocities above a few kilometers per second. If the energy budget stays impossible for solar heating alone, if the chemistry refuses to fit any known comet composition, then we'll have a decision to make. Do we expand the category of natural comets to include behaviors we've never seen? Do we propose exotic ice compositions or fragment geometries that preserve the natural explanation? Or do we seriously evaluate the possibility that some interstellar objects might not be natural at all? Loeb argues for humility. Keep all hypotheses on the table until data eliminates them. Don't reject artificial explanations reflexively because they sound like science fiction. Test them, measure them, let the observations decide. The Galileo Project, which Loeb heads, exists precisely for this purpose, to collect high-quality data on anomalous phenomena without prejudging the outcome. 3. I-ATLAS fits that mission perfectly. It's anomalous, it's documented, it's testable. The mainstream counters with Occam's razor. The simplest explanation is usually correct. 3. I-ATLAS is a comet. Comets are made of ice and dust. Solar heating drives out gassing. Large dust particles explain the anti-tail. Carbon dioxide explains the activity at this distance. The nickel-to-iron ratio is unusual but not impossible. The jets will eventually smear or fragment or reveal their natural origin when we get better data. Adding artificial technology to the hypothesis introduces unnecessary complexity. Extraordinary claims require extraordinary evidence, and we're not there yet. Both sides agree on one thing: keep observing, keep measuring, keep publishing. The data will decide, and the data is coming. December 19th is the target. Observatories in Chile, Hawaii, Australia, South Africa, Spain, Italy, Thailand, Japan, and the United States are coordinating. Professional and amateur astronomers are sharing images in real time. The Minor Planet Center is updating the orbit solution with every new observation. The community is engaged. This is science at its best: collaborative, transparent, competitive, and driven by evidence. What happens if 3 I-ATLAS turns out to be entirely natural? We learn that interstellar comets can have compositions and behaviors wildly different from solar system comets. We learn that carbon dioxide can dominate at distances where we expected water. We learn that large dust particles can create persistent anti-tails under specific conditions. We learn that jet collimation can occur through topographic effects or fragment clustering. We expand our understanding of how comets form in other stellar systems, what materials they contain, and how they evolve over billions of years in the interstellar medium. That's valuable. That's discovery. What happens if some anomalies resist natural explanation even after exhaustive analysis? Then we have a genuine mystery, an object that doesn't fit the box, a data point that forces us to reconsider assumptions. Maybe interstellar space contains ice compositions we haven't thought of. Maybe fragmentation produces geometries that mimic intact bodies. Maybe there are natural physical processes that produce collimated jets over million-kilometer scales that we haven't modeled yet. Or maybe, just maybe, we've detected something that was made, not formed. Something that navigates, not drifts. Something that's observing us as we observe it. That's the edge of science. The place where data meets interpretation. The place where careful measurement collides with bold hypothesis. The place where careers are made or broken based on what the next observation shows. 3. I-ATLAS sits right on that edge. It's close enough to natural to avoid immediate rejection. It's strange enough to warrant serious attention. It's well documented enough to survive scrutiny. And it's gone soon enough that we can't afford to wait. The clock runs. December 19th is 28 days away as of November 21st. When the most recent observations were published, every clear night counts, every spectrum matters, every image adds a piece to the puzzle, the astronomical community is mobilized, the data is flowing, the analysis is ongoing, and in the background, quietly, the question persists. What if? What if 1I, Oumuamua, wasn't an anomaly but a scout? What if 2, I Borisov, was natural, but 3, I Atlas isn't? What if interstellar space is full of objects, some natural, some not? And we're just now developing the technology to tell them apart. What if the galaxy is older and more populated than we assumed, and manufactured objects drift between stars just as often as icy rubble does? These aren't mainstream questions. They're fringe. They're speculative. But they're not unscientific. They're testable. And 3, I Atlas is the test. Avi Loeb closes one of his November posts with this line: "Figuring things out through the collection of data resembles the work of a detective. With the flood of data on 3 I Atlas in the coming weeks, leading to its closest approach to Earth on December 19th, 2025, we should be able to figure out its nature. The public resonates with evidence-based science as long as the scientists show the humility to learn something new. The humility to learn something new. That's the challenge. That's the opportunity. 3 I Atlas offers both. It's an interstellar visitor, confirmed by trajectory. It's active, confirmed by imaging. It's unusual, confirmed by multiple anomalies. And it's observable, right now, for anyone with a telescope and the patience to track a magnitude 11.5 object moving slowly against the stars. If you're in the southern hemisphere or near the equator, you have a better shot. If you're farther north, the pre-dawn window is narrower but still there. Set your alarm. Point your scope at Virgo. Find the fuzzy dot with the tail. Take your own images. Submit them to the Minor Planet Center. Add your data to the pile. Become part of the discovery. Because that's what this is. Discovery, not conclusion, not final answer. Discovery in progress. And the most important discoveries are the ones that surprise us, that don't fit the template, that force us to expand our categories and question our assumptions. 3, I Atlas is doing exactly that. It showed up unexpected. It behaved unexpectedly. It survived perihelion unexpectedly intact. It's producing jets unexpectedly collimated. It's emitting gases unexpectedly skewed toward nickel and carbon, and it's leaving in a few months, taking its secrets with it unless we capture them now. The November 15th image from Tirasak Thalawang sits on a server in Thailand, showing a bright anti-tail and 2 regular tails, all emanating from a single fuzzy nucleus, all defying the simple comet narrative. The November 9th image from Niebling and Buchner sits in Germany, showing million-kilometer jets that shouldn't be that straight after a month of rotation. The November 11th image from Jewett and Liu sits at UCLA, showing a single intact body that shouldn't have survived if it lost 13% of its mass in 1 month. The ESA data from ExoMars sits in the Minor Planet Center database, the first planetary orbiter contribution, proving that we can triangulate interstellar objects from multiple vantage points and nail their trajectories with unprecedented precision. The JWST spectrum sits at STSCI, showing carbon dioxide dominating the gas budget in ways that match theory but clash with the jet observations. The VLT nickel detection sits in the archives, waiting for someone to explain why iron is missing. The Swift hydroxyl detection sits in the NASA database, confirming water activity that's strangely weak for an object this active. And the Hubble size limit sits in the science paper, capping the nucleus at 5.6 kilometers, too small to power the jets through solar heating alone. All the pieces are there. The data exists. The observations are published, the calculations are public, and the conclusion is uncertain, genuinely uncertain, not because scientists are hiding something, not because the data is bad, but because the data is strange, and strange data takes time to understand. Maybe 3. I Atlas is a completely natural comet with an unusual composition that creates unusual behavior. Maybe it's a fragmented object where the pieces are too close to resolve, but collectively explain the surface area problem. Maybe it's a comet with a different volatile mix that sublimates differently than we modeled. Or maybe it's something we haven't seen before, something that doesn't fit the comet category at all, something that requires a new category. The answer is in the data. The data is coming. December 19th, peaks. February 26 delivers JUICE results. March 2026 adds Juno's flyby. By mid-2026, we'll know more. Not everything, but more. Enough to constrain, enough to test, enough to choose between hypotheses. And if the data still doesn't fit, we keep looking. We propose new mechanisms. We build new models. We test again. That's how science works. not by declaration, but by iteration, not by authority, but by evidence. 3. iAtlas doesn't care what we think. It's a comet, or it's not. It's natural, or it's not. It follows the laws of physics either way. Our job is to figure out which laws apply, which mechanisms are active, and which category it belongs in. If we get it wrong, the data will correct us. If we get it right, the data will confirm. Either way, the data is in charge, not our preferences. And that's the beauty of this moment. We're watching data-driven science in real time. No final answers yet, no settled consensus, just observations piling up, calculations being checked, hypotheses being floated and tested and refined. It's messy, it's public. It's exactly how science should be: transparent, competitive, evidence-based, and open to surprise. So here's where we stand on November 17th, 2025. 3 iAtlas is outbound from perihelion. Currently about 1.43 AU from the Sun, 2.16 AU from Earth. It's in Virgo, magnitude around 11 to 12 TORs, observable in pre-dawn skies with moderate telescopes. It displays a persistent anti-tail pointing toward the Sun, regular tails pointing away, and complex jet structures extending up to 3 million kilometers. It rotates every 16.16 hours, but the jets don't smear. It lost at least 13% of its mass near perihelion, but appears intact. It emits nickel without iron, carbon dioxide without much water, and shows a carbon to oxygen ratio 10 times higher than normal comets. 12 documented anomalies, probability less than 1 in 10 quadrillion if all are random natural occurrences. Closest approach to Earth in 32 days. Peak observation window opening. Data flood incoming. The evidence that matters is the evidence we're collecting right now. Spectroscopic velocities will arrive soon. Jet evolution will be tracked day by day. Surface brightness profiles will refine the nucleus size estimate. Spacecraft flybys will add non-Earth vantage points. And by spring 2026, we'll have enough data to write the definitive paper on 3 iAtlas. That paper will either explain everything naturally, or it will admit that some anomalies remain unexplained. Either outcome is science, either outcome advances understanding, but for now, in November 2025, we're in the observation phase, the data collection phase, the document everything because it's never coming back phase. And if you look up before dawn in the coming weeks, point your telescope at Virgo, and catch that fuzzy dot with the impossible tail, you're part of it. You're observing an interstellar visitor that might be the strangest comet we've ever seen, or might be something else entirely. You're doing astronomy. You're contributing data. You're participating in discovery. That's the final line, not a conclusion, not a summary, but a cold, hard fact buried in the trajectory data, waiting in ESA's archive, published November 14th, 2025, ExoMars. Trace gas orbiters observations from Mars, 30 million kilometers from 3 iAtlas on October 3rd, refined the comet's predicted position by a factor of 10 and became the first astrometric measurements from a planetary orbiter ever accepted into the Minor Planet Center database. We crossed a threshold. We proved we can track interstellar objects from multiple planets. We proved triangulation works across tens of millions of kilometers. We proved our network is ready. And 3, iAtlas proved that interstellar space sends us objects we don't fully understand, yet